Thank you for this kind of embarrassing introduction. Do you all have a handout? Okay. Yeah, the handout, it's a tiny bit retro, but you can sort of get into the spirit of things. If you have an equally antiquated device like a pencil, you can pencil questions and remarks, and then you'll remember them for the question period. So there's some advantages to killing all these trees. All right, so the stochastic constraint-based grammars for Hausa, verse, and song. This is fundamentally about singing in Hausa, which is a Chadic language spoken in various countries in West Africa. The line that I want to put forth here is that it's a layered procedure, and that there's at least 3 layers. You begin with poetry. So you arrange words into lines in lawful fashion, respecting a meter, which I'll describe. Once you have the poetry, you rearrange it. You rearrange it into a musical rhythm, which will resemble the poetic rhythm, but as we'll see, is not the same thing. So that's the second stage. And in the third stage, we reach entities that we can actually observe and measure in time. The durations of the notes in this sung rhythm are realized in an essentially indirect way through physical duration, and we'll try to elucidate that mapping. So that's the 3 layers, and I'm going to provide linguistic analysis of all 3 layers. And there's evidently, I've been talking to people all day and really enjoyed it. There's evidently a fair number of people here who know quite a bit of linguistics, so don't feel patronized if I tell you what an analysis is. Maybe tells my ideological viewpoint. What is an analysis? We have representations, they are formal objects. We have constraints, and we have some kind of grammatical architecture. At the very least, it ought to summarize a body of existing linguistic data with reasonable accuracy. It could, in principle, though will not today, make predictions about novel data that we could gather from similar speakers or singers. And also, I would like to imagine that a good linguistic analysis can serve as a sort of platform or guiding framework for experimental study or all sorts of study as carried out by cognitive science. So that's where we're trying to go. And in fact, that's all the more we're going to go. We're going to try to get a working analysis for the 3 levels. So why on earth am I talking about Hausa poetry and song? I cannot speak a word of Hausa. I have met Hausa speakers, and they're very nice, but pretty much the whole empirical side of this talk is coming from my research collaborator, my senior colleague at UCLA, Professor Russell Schuh, who fortunately for me is one of the world's leading experts on this language, including on its verse and song. So let's talk just a tiny bit about the ethnography. The Hausas are not like us in English departments. You don't pick up a book and read it silently or recite it. It is inevitable that poetry is sung. Even if you pick up a book, you've got to find a tune, because that's the way that it's got to be realized. And I suspect this is completely the norm. It's only really decadent societies that ever had the idea of reading poetry. Okay. So that's what happens. So in fact, we have to study the poetry in its sung version. There is no other overt version. The phonological basis for the rhythms of Hausa poetry can be found in a fundamental distinction that's proved extremely useful in phonological theory, the distinction between heavy and light syllables. A syllable is defined as light if it ends in a short vowel. So a syllable like ta is a light syllable. If a syllable ends in a consonant or has a long vowel, Hausa has both kinds, so tan or ta, it is defined as heavy. This is not unique to Hausa. In fact, it's found in quite a few similar systems, including the classical languages, ancient Greek, Latin, and Sanskrit, Arabic, Persian. So it's a fairly common principle. The other bit of phonological background is it will be extremely convenient for us to think of a heavy syllable as composed of two moras. A famous phonology joke, they're not very funny phonology jokes, but a mora is defined as that of which a heavy syllable consists of two and a light syllable consists of one. So you might think of ta in a heavy syllable as having the moras ta and n. Ta is ta and a, whereas ta is just itself. So once you have the heavy and light syllables, then you can define a meter. A meter is realized as a characteristic pattern of lights and heavies. So in the material I distributed for intrepid people to look at before this talk, you can hand in your homework to me later if you would like it graded. You are given a meter whose basic pattern is what you see in 2. Oh, and the symbols. The little, look up, this little thingy is called a breve, and it means light syllable, and this thingy is called a Metron, and it's heavy syllable. So if I may recite it with short little does for breves and longer ones for Macrons, one of the meters, catalectic mutadaric, is da-da-da, 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 da-da. Or you can substitute for any of the datas one single heavy. So it could be da-da, da-da-da, da-da, da-da, or any of the 8 combinations implied by the list you see there. There's a whole bunch of meters in Hausa. And if you want to learn about them, go to the work of my colleague Schuh. He's written articles about quite a few of them, and I think pretty much all of them get covered somewhere in his research oeuvre. Today I want to focus on just one single meter, and that's the rajaz meter. Rajaz is a word borrowed from Arabic, but Arabic really, this is basically a Hausa meter, and it's just an accident that they use Arabic terminology to describe it. Let us cover the basic observational facts about the rajaz. So here come the facts. You can write a rajaz in either dimeter or trimeter. And if it's a dimeter, it means that each line has 2 metra, which is the plural of Metron, terminology taken straight from the literature on Greek metrics. They too actually have these kind of metra. The metra in rajaz are interestingly variegated. There are 5 major types and a whole bunch of minor types I'm not going to tell you about. But the vast bulk of the data is covered by the 5 major types. We have a little corpus that we've been working with to understand the rajaz. It's 11 poems, about 2,500 lines. So from the spreadsheet, counting up the Metron types, it's what you see in 9 on your handout. Basically, there are 5 types, but with minor exceptions. There's only 4 of them that occur as a first metron, and a different 4 that occur as a second metron. And you see some counts and frequencies in the chart. The 2 metra of a line are, we have checked, statistically independent. You can freely choose one, freely choose the next, and the result, provided you've made a legal choice, the result will be a legal rajaz line. So if I put together 2 instances of da-da-da-da, I would get bottom of page 2, da-da-da-da-da-da-da. That's a typical rajaz line. But I could also pick differently, da-da-da-da-da-da-da, da-da-da-da-da-da-da-da, and so on. Let us look at some, I promise there will be raw data. This is a poem called Tutochin Shehu, written in 1955. And what you see there is your standard linguistic display. I've divided the words into syllables. And if you go back to the criterion of syllable quantity, I have properly labeled each syllable with the macron or breve according to whether it is heavy or light. And for convenience, I have put a slash in between the 2 metra of each line. Okay, so that's the text. And I want to make a little illustration to you to make a point. If you just ask a Hausa speaker to read the text, it is very unlikely to sound like poetry. Historically, we've had a lot of Hausa speakers around the department. At the moment, it's 0. So you are going to hear American accented Hausa from Russell Schuh. But he's a very fluent speaker, but he does have a little bit of an American accent. Listen.
Wakila na mance wani, ka san hali da tunani, balle kamar miskini, wakila ba shi anini, a san da yayi tunanniya.
Okay, so that's what it sounds like as spoken language. Okay. Now let's try to start generalizing about the data, and then once we've generalized, we can start to theorize a little bit. Here's the first point. The metra are characteristically hexamereic, 6 mores. That's true for all but one of the primary metron types. Then what about the one heptamereic one? Actually, if you flip back to 9, so there they are, da 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 da, 1 2 1 2, that's 6, da 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 2 2 2, that's 6. And the exception is the 4th one, da 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 da. That's going to be 2 2 1 2 7. Okay. Why that heptamereic foot? Well, you actually have to know more about Hausa metrics in general. In hexameter, there is a license such that at the beginning of the line, if the pattern expects a light, you are permitted to use a heavy instead. Okay, so that's just a special license awarded to the poet. Let's just take it at face value. We don't have an explanation for why this should be so, but it is so. And we will say that under the heavy equals light initially, the heptamereic foot is going to be counted as hexamereic and thus fit into the generalization. And that works fine because it explains why it's so rare in the second metron. Okay, that's fine. Going back to 9, you will see that, of course, every metron ends in a heavy. So that's obligatory final heavy. And there is a statistical generalization that, I need to give you the terminology. You know English iambic pentameter? Da-da, 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 da-da. That terminology came from Greek, where they have a foot which is light heavy. And if you put 2 of them together, you get an iambic metron. So the iambic metron, plus its heptamereic partner, which is sort of the moral equivalent of iambic, they are almost half the data. They seem to be the preferred metron type. So that's generalizations that we need to handle. So that's just a tiny bit of facts. Let's see what we could do with a tiny bit of theory. The goal so far is to implement 3 generalizations: Hexamer Olicity, obligatory final heavy, and iambic preference. So let's give this a widely used tool in the analysis of meter and rhythm is the metrical grid. Proposed by various people in the 70s, probably the most famous publication that puts it forth is this widely cited book, Lerdahl and Jackendorf, A Generative Theory of Tonal Music, which has led to quite a bit of follow-up work. What is a grid? Well, it's the X's you see in 13. For concreteness, I've filled the grid with an actual line of rajaz. But how do you interpret a grid? It's columns of X's. The height of a column is the strength of the beat. So I might recite the grid myself intuitively by saying da 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 da. Got it? Yeah. But actually, the rows of the grid are relevant as well, and this can be shown by a wide variety of phenomena. The lowest row here is the fastest of a set of intersecting periodicities. So it is the beat level that goes da 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 da, and the next one up is the beat level that goes da 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 da, and the next one up is the one that goes da da. So you just put them all together and you get the overall pattern. So that's the grid, and as I said, I have used little lines to indicate the affiliation of an actual line of rajaz, a very simple one with all iams. to the grid. So that's a representation. Now what about, I mentioned, did I? No. Constraints. Constraints are emerging as kind of the common currency of linguistic theorizing. I see the philosophy of constraints as an attempt to kind of atomize analysis. We want to get linguistic complexity to emerge from very simple ingredients that interact in complex ways. The constraints often conflict with each other, so it's the delicate arrangement of priorities amongst constraints that leads to the complicated patterns that we see in human languages. This is going to be the framework that I'll put forth in a sec. Is going to be a stochastic framework, so it's gradient, and so constraints can vary in their strength. Okay, so here's the story. Entities that violate constraints get lower probabilities assigned to them than constraints that don't, and moreover, if you violate a constraint that is a powerful constraint, then your probability is lowered more than otherwise. We need some constraints. First of all, what about Hexamer Olicity? The grid is, of course, designed for this very purpose. What we're going to want is to have a one-to-one correspondence of moras and grid slots. So let's implement that concretely with two, it turns out, very powerful constraints. A star stretch, star squeeze. Oh, asterisks in linguistics means this is bad. Okay. Star stretch means don't put a mora in more than one grid column. Whenever you make a constraint, you have to specify precisely the conditions under which it's violated. We'll say 1 is the max, and for every extra one you add, that's a violation. Same with squeeze, the moras should not be sharing their grid columns, so we'll define that as saying 1 is fine, every mora extra that you add in incurs a violation. So little diagrams showing abstract violations of star stretch and star squeeze. That's Hexamer Olicity. What about the other two generalizations? As you can see, the grid is attempting to leverage a kind of equivalence between, not equivalence, a kind of natural relation between rhythmic prominence and syllable weight. There's a lot of phonological and experimental evidence that heavy syllables are just perceptually more prominent. Okay, so it makes sense that in a language like Hausa that has a clear heavy-light distinction, the heavy syllables would be used to manifest rhythmically strong positions. So let's try to turn that into very simple constraints. If you go back to 13, you can see that I have labeled the levels of the grid, weak, strong, and super strong. So let's use those in the constraints. Strong is long. Assess a penalty for any strong or stronger grid column that does not initiate a heavy syllable. Super strong is long. Assess a penalty for any super strong grid column that does not initiate a heavy syllable. And long is strong goes the opposite way. If you have a heavy syllable and it fails to be initiated in a strong grid column, that incurs a violation. Okay, now where is this all heading? Super strong is long requires that the super strong positions, that is the last two grid columns of the Metron, be initiate a heavy, and that of course translates straightforwardly to the requirement that metra end in heavy syllables. That's fine. Strong as long is going to be a weaker constraint, as you'll see once we implement the grammar. It is responsible for the mere preference for iambicity. That is, when you have da-da, da-da, the first heavy falls into the second grid column of the grid. Long is strong is more subtle, and I'll get to it in a second. Indeed, I'll get to it right now, but you need more data. Here's a slightly more subtle pattern. In fact, it took a while for us to notice it. Preamble. Our data were deeply depressing to us in that once we collected 11 different poems, we found that they were all using different mixtures of Metron. It looked like just a bitterly frustrating, the poet gets to do whatever she wants thing. And indeed, to some extent, we're still in this boat. But what we figured out with greater scrutiny of the data is that the arbitrariness, the poem-specific patterning, seems to be confined largely to the second metron of the line. So that, as far as we can tell, is an aesthetic choice made by the poet, possibly influenced by the tune. We'll get to that. In contrast, in the first metron, there is a kind of orderly pattern that is based on frequency. The iambic metra, that is the combination of da-da-da-da and da-da-da-da, they are always the most frequent. In second place is the one that goes da-da-da-da. This is in 17. And in last place is da-da-da. The remaining possibility, da-da-da-da, is completely illegal in initial position, and we don't understand why that is true. But let's just look at these three. That's the frequency relation. But now, here's the cool thing. It is virtually always respected throughout the corpus, but it is respected in different ways, sometimes by making every single metron iambic, sometimes by having rather modest distinctions. This varies from poem to poem. But the implicational relation, iambic, more frequent than da-da-da-da, more frequent than da-da-da, that holds good across poems. In fact, it's even stronger than this, because the data include a further aspect of complexity. The poems are written in 5-line stanzas, and the poet gets to make a different choice for final metron in the 5th line of a stanza than he or she does in the first 4. Nevertheless, the implicational relationship of relative frequency that I described to you holds good for the stanza final metra. So look at 18. Here's your graph. See, you can do graphs on handouts. You see the titles of the poems, and tilde F means non-final and F means final, and with a couple little glitches that are unlikely to be more than just statistical accidents, the implicational relationship holds good. Okay, so now we ask, can we get this relationship with some kind of analysis? Let's look more closely at the 3 crucial kinds of metron and look at the constraints where they differ in their violations. In 19, you see that the iambic metron is perfect. No violations of strong as long, because both strong positions, the 2nd and 5th, initiate a heavy syllable. Moreover, no violations of long as strong, because both heavy syllables are initiated in a strong position. Page 6, you see da-da-da-da. Now there are violations. So that's a bad place for a page break. Strong as long is violated because the first strong grid position, number 2, fails to initiate a heavy. Long is strong is violated because that first heavy fails to be initiated in a strong position. Finally, what about da-da-da, the 3 heavies? Here you have the most violations. That is, the circled strong position fails to initiate a heavy, and there are 2 heavies that fail to be initiated in strong position. So that's the scheme. Now, what we want to get out of this, well, you see what it is. It's a subset relationship. A subset relationship of constraint violations from which we hope to deduce a difference in, say, complexity and hence frequency. Okay. Well, to do that, we need the final ingredient in the analysis, which is the grammatical framework. And this is going to be Maxent grammars, sometimes more properly called Maxent optimality theory grammars. These originate, oh good grief, if you really work, you can get this to originate in the 19th century. But I would say it's Paul Smolinski's work that got this up and running. More recent references applying it directly to phonology, Goldwater and Johnson, my work with Colin Wilson. I feel a little bit funny telling this to cognitive scientists because I suspect this is going to look really ordinary to you. And it's a cultural difference that makes this radical in linguistics. I personally feel it's the best thing since sliced bread, and I go around from university to university trying to sell it. But maybe you'll have a so what reaction if you're going. Listen, here we go. There's constraints. Every constraint has a weight, which is a non-negative real number reflecting its strength. We set up a possibly extremely large menu of possibilities from which the grammar selects. This is called gen. It is a full set of logical possibilities implied by the representational system. Our system is very simple. We have two symbols, light and heavy. Let us suppose that gen consists of all strings of light and heavy. This is a countable infinity of candidates, but it turns out that you will get perfectly accurate results if you only consider the shortest, say, 64 of them. That's what we did. You could show this in the math. So it's computationally tractable. Then comes the math. A well-studied mathematical formula does the following task. You take the candidates, their pattern of violation of the constraints, and the weights of the constraints. They are all plugged into the formula that you see there, which is basically just simple algebra of various kinds. And what comes out is a probability. Right? So from candidates, weights, violations, you calculate a probability distribution over candidates. When you do this, when you use this to do linguistics, what almost always happens is that the vast majority of candidates get a probability so close to zero that we're willing to call it zero. In fact, that happens here, as you'll see. Where you're working with a system that has frequencies, variation, optionality, it seems to be an excellent tool because it plugs us into the language of probability theory for linguistic analysis. Okay, in particular, let's go back to the little problem we were working on. We have a subset of constraint violations in the three Metron types that have this implicational relationship of frequencies. It is pretty straightforward to show from the formulas in the formula in 20 that if this is 21, if candidate A has a subset of the violations of candidate B, then A necessarily gets higher or equal probability as B. So the claim is this is exactly what we want. We've got the subset relationship, and empirically speaking, the frequencies are all over the map, because each poet is writing his or her poem with different weights. But what is guaranteed to come out, if this is the right constraint system, is the implicational relationships about frequency. Does that make sense? Okay. Well, all right, so just for concreteness, let's put together a full analysis for this poem, Tutochin Shehu. This is done with a spreadsheet, it's not all that big. We have a bunch of constraints that I've told you about, and then time for the stupid constraints. We cannot explain the poet's arbitrary choice for a particular metra in second position, so we will merely describe it with constraints saying, go ahead, use this metron in the second position. I also mentioned the mystery of why da-da-da-ta is very rare in first position. We'll just stipulate that. So there's various ways you can set the weights. There's a lovely software, not written by me, but available from my website, the Maxent Grammar tool. Stephanie uses, actually. Or there's stuff in Excel, or you can use R, et cetera, et cetera. The algorithm is convergent, so no matter how you do it, you'll get basically the same answer. So the best fit weights are what you see on page 7. Star squeeze is very strong, as you might think. super strong is long is very strong, star stretch is very strong. Something specific to this poem, strong is long in the last metron. The stupid one, don't start the line with da-da. A ban on 3 lights in a row, which is found in other languages as well. A stupid constraint, use da-da-da as the last metron. Then little subtle ones that are simply tweaking the frequencies. Strong is long, don't employ the convention of heavy for light substitution. And the very weakest one at the bottom is long is strong.
Bruce, can you say a little more? What are the weights? What's the algorithm doing with the weights? Is trying to minimize or maximize something?
Oh, yeah. You compute the probability of every candidate, and then you take the log probability, the log of those probabilities, and sum it up. Okay. So I think this is the standard thing for computer. You're maximizing the log probability of the data.
Okay.
Yeah. Okay. And maybe not that surprisingly, because there's a lot of parameters for just a couple hundred values, but the fit seems to be just fine. The data points represent 1 gen of 64 types for each of the 4 logically possible combinations of first, second, metron, stanza final, stanza non-final. And given that the points are on top of each other, I have to tell you that the vast majority of the data points are sitting pretty much on top of the origin, which is what you'd expect. Okay, so that is the structure of the meter. We have finished the first layer. Let's move on to singing. Of the 11 poems in my colleague's collection, 5 come with a recording of someone, possibly the poet, singing it. And here's the interesting generalization over the sung versions. As far as we can tell, nobody sings it straight. Maybe I should tell you what straight would be. Look at 25. If you just went Kano ta'a dushan dabo da-da, 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 over and over with iambic metra, that would be singing it straight, and nobody does it. They all instead kind of remap. They remap the metrical rhythm into a related but distinct sung rhythm. And I want to give you 3 cases of how they do this. First, for Tutochin Shehu, the remapping consists of splicing in additional grid material such that the original 6/8 time, in musical terms, is remapped as 9/8 time. So if that doesn't make sense, just look at the grid. The italicized X's are what are put in. So instead of doing da-da, 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 the singer is doing da-da, 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 da-da. I'm conducting, by the way. Da-da, 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 da-da. So it's 9 with 3 threes. So let's listen to an actual Hausa singing this.
Kanota Vishayavo, do one that can be there. Akwai shi can ruwa katambata famantiwo domin fada ta gaskiya.
Okay, that's your first remapping. Another one by Hawa Gwaram takes a different approach. The number of X's in the grid is 12, just like in the original grid, but the location of the upper level strong beats has been shifted in a curious way. So instead of musam kudim mumutara, so see what happens instead is da 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 da. I'm conducting in da 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 da. That's now, she's not quite as fluent and puts in a couple pauses, but I think if you listen to this, you'll be able to hear it. So da 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 da. So here's sort of an empirically interesting thing. The iambic Metron that you get at the beginning, da-da-da-da, was perfectly rhythmically normal in its metrical context, but is now syncopated in the sung context. There is a funny thing about this poem. The metra that the poet selects all end in heavy, heavy. And if you go back to the sung grid, I think there's a reason for this, that by having heavy, heavy at the end, you always get a heavy to fill the rightmost super strong position. So we suspect that's not an accident, that poet choice of Metron is determined sometimes by song. One more, Kokon Mabarata. Here, this is for us the most radical remapping. It's remapped onto a 16 position grid that in music would be like 4/4 time. So instead of da-da, 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 it will sound roughly like da-da, 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 da. Listen to this guy.
Ubangiji kai fatiya ka bani dama na tsiya yaban ma'aiki na biya na ba da kwazo na tsaya akan ta ba a goce ba.
Okay, so that's particularly striking because these kind of isochronous syllables still have their heavy and light quantities that they inherit from the meter. Well, okay, analysis of remapping. I think this is a fascinating question, and I wish we had more answers for you. But we can at least put forth some possibilities. The most primitive theory of remapping would be to say the following. You write a poem in rajaz using the rajaz meter. You throw away the meter. You keep the text. You sing the text to a different grid. That would be a very simple procedure. And so the mappings are just syllables to grid. You don't need to go grid to grid. This is unlikely to be true. And the reason it's unlikely to be true is that many Hausa poets they're like bards. They can improvise on the spot. They produce legal poetry in real time. So that raises very interesting questions that it would be fun to study. Is it possible for a poet to do the mental computations that would be required to satisfy two distinct grids at once? Maybe. Or alternatively, does the poet somehow short-circuit the process, make up crazy rules that would permit him to put syllables into the sung grid that nevertheless manage to be legal rajaz lines? This is the topic of a smallish but expanding literature in metrics. The whole question of how many levels are present in sung verse and how they relate to each other. Last layer, phonetic duration. I'm going to issue stirring propaganda. You'll be stirred, but a great frontier of linguistics and phonetics, something that we absolutely ought to be doing, and progress is slow, is the creation of grammars for phonetic realization. Ideally, linguists make rule systems and they try to predict the structure of languages and the output of speakers. We should be able to predict the behavior of speakers down to the level of things we can measure, like milliseconds of time, hertz of pitch, millimeters for articulative position. It is very likely that such grammars will be probabilistic because speech output naturally has a great deal of variation. In my youth, there were brave efforts to write complete grammars for phonetics, notably the MyTalk system at MIT, or Beckman and Pierre Humbert's system for producing pitch contours in Japanese. As far as I can tell, this is not all that active a research topic right now. I was just at the International Congress of Phonetic Sciences in Glasgow, and as far as I could tell, nary a paper addressed this question, which is, of course, the theoretical question: how do people talk? What's the algorithm for talking? Okay. The problem is vast because every measurable physical parameter has been shown by the very large and competent research literature in experimental phonetics. That literature shows that every physical parameter is influenced by multiple structural factors, and that every structural factor is realized in multiple physical parameters. You might think for heaven's sake, why don't you just go with what Siri does? And I think the answer there is that of course, the guys who do industrial linguistics are extremely smart and they're doing very well, but I don't think what they're doing will answer the scientific question, because what they're doing is to collect huge numbers of building blocks of varying length and concatenating them to get the synthesized result. That can't be exactly what people do, because people are able to pronounce completely novel words and utterances that follow the pattern of the already existing ones. All right, so we've got to solve the problem, and let's get started. What should the linguist do? The linguist should discover the schemata. The linguist should discover what constraints are like, make general hypotheses. The grammars are going to be vast, but they are not going to be handcrafted. We will adapt existing theoretical and computational work in learnability such that the language learner could learn the phonetic grammar from exposure to data. Observe that this may be the very last thing that gets learned. It's incredibly hard. It takes the kid 5 or 6 years. Okay. And lastly, vast machines, oh, for heaven's sake, quantum computers will realize our enormous learned grammars and produce speech indistinguishable that of people. Okay, well, just very speculatively, what could we say about such grammars? I believe that the research literature in phonetics reveals a pervasive principle of phonetic realization, and that is the principle of compromise between conflicting targets. What you observe is the result of a contention between conflicting goals. And let me give you just one example, a well-known one for 40 years. If I take a word like some, and then I add another syllable to it, like, say, to make the word summon, or yet another syllable to get the word summoner, the durations, and there's serious work that does this. I just measured myself to get my handout done. But look, sum is 546 milliseconds long by itself. It gets shorter in summon and shorter still in summoner. The word gets longer, but not by much. Okay, 546, 570, 580. So the silly metaphor that I would like you to ponder is stuffing a stretchable sack with compressible sponges. The syllables can be squeezed if necessary, and what squeezes them is some urge for the word not to be too long. This happens all over the place. The grammatical formalism for doing this has already been established, or one that can do it, by Edward Fleming in a lovely paper from 2001. He does it not in Maxent, but in a slightly simpler version that generates just one single output. That's fine for our purposes. What he does is to take each linguistic category, give it a quantitative target value, and let the constraints penalize deviations from this value. So for instance, if it's duration, you could take the deviation between target and candidate value and measure it in milliseconds, whatever. Fleming suggests that the deviations ought to be squared deviations. This seems to work better mathematically and give you better results when you model data, so we'll do that. Now let's move on towards duration, sponges, and sacks. We can have a constraint like star squeeze. The violations are the square of the difference between the candidate value and the target value, where the candidate value is greater. Star stretch would be the opposite. It's how much it falls short. We're going to have targets for several categories, and for completeness, we'll give each one a stretch and a squeeze constraint. So everything is construed as simultaneously a sponge and a sack. Since you square the difference, the profiles of constraint violation form half parabolas. So in 35, you see the half parabolas for an abstract constraint. And you can see it's asymmetrical because the weight of stretch is twice the weight of squeeze. Okay, let's do rajaz. We will set up duration targets for 4 categories. syllable, mora, grid column, and Metron. And we will see that they conflict with each other. Each one will get its own stretch, and star squeeze constraint. And we will take the Maxent and apply it to Fleming. We are going to assess the violations of candidates and apply the learning algorithm and find the weights that best fit the data. So in the end, the system is going to output not one single predicted value, but a probability distribution over values. What about gen? Well, gen is truly frightening. If you're talking about duration, the number of candidates should be an uncountable infinity. Let's try to make our lives a little bit easier. Following work by Paul Boersma, we can maybe reify time a little bit. Let's just we'll only consider every 10 milliseconds as a candidate. So we'll just approximate time so we can get a countable infinity. And of course, it is safe under present circumstances to limit the durations in our candidates to the durations, more or less the ones that are observed in the data, which go from 80 to 490 milliseconds. We have a training set for setting the grammar up. We measured the durations of 200 lines, all the syllables in 200 lines of Tutochin Shehu. And we hit a snag that we would eventually like to overcome, but that hasn't happened yet. The last syllable in the Metron is very hard to measure. It's often pre-pausal and it sort of fades out in a difficult way. So to make our lives easier at this preliminary stage, we're just leaving it out and we're not trying to model it. So what we're actually using as our target is sort of like a hemi-Metron rather than the full Metron. Okay. Now, how do we learn the grammar from the data? This turns out to be quite hard. Learning the weights, if you know the targets, is easy. But how do we learn the targets? My student, Michael Lefkowitz, who's applying this model to spoken language data at UCLA, has tried searching for the targets in the same way that you search for the weights, and hit a snag. It turns out the data underdetermine the solution. It's hard to find a good working solution. Let us go out on a limb. Suppose it is the case that the targets can actually be learned from some surfacely observable property of the data of their distribution. The guess, we've tried different things like the mean, the median. Let's try the mode, the most frequent value of a smooth distribution. This surely is not the best fit grammar. The conjecture is that it will work well enough for our purpose. Let's put this all together. Following the smooth mode criterion, the durational targets for mora, syllable, grid column, and hemi-Metron are as in 42. If you plug these in, calculate the constraint violations, fix the weights according to best fit, you will find that you get positive weights for 4 stretch constraints and 3 of the 4 squeeze constraints. It turned out that squeeze hemi-Metron is best fit with a value of 0, so it's essentially not there in the grammar. Well, how well does it work? It works sort of well. In 43, the nice smooth curves, of course, are the ones that are predicted by the theory, and the slightly bumpy curves are the ones of the data. So we're getting distributions of syllable duration that are a reasonably good match to the distribution seen in the real world. More interestingly, though, I think, are an effort to look at the actual qualitative generalizations that are present in the data and see if the grammar is getting them. I mentioned that phonetics is compromised, so let's take a look at 4 such compromises and see how the grammar derives them. First compromise. Heavy syllables are not twice as long as lights, okay, by a substantial margin. That is pretty easy to get in the grammar. It is a compromise between the rather low target for syllables and the doubled value of the mora target. So that's both observed in the data, predicted by the model, things seem fine. Second, the heavy syllables in an all-heavy metron should be longer than the heavy syllables in one in which you only get 2 instead of 3, actually 1 in the domain that we analyze, leaving out the last. So in da, 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 you should get longer heavies than da, 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 and da, 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 da. Why so? Well, we just established that the light syllables are more than half the duration of the heavy. They are chubby moras. And so when you have heavy syllables that must share their metron with chubby moras, they are crowded and they shrink. So that is empirically true. The effect is there in the data. The model gets the effect qualitatively, but it doesn't get a big enough difference. 47 looks at the heptameraic feet, da, 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 da. And it should have the shortest syllables of all. That is, this, sorry, I said foot, I should have said metron. The heptameraic metron has the most phonological material. It stands to reason that it's going to be squeezed more. So indeed, the second heavy of that kind of metron is indeed shorter than the heavies of the da 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 and da 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 da. You see the observed difference, and you can see that the model is predicting a difference, but again, it's not big enough. The last one is the most subtle. What about the 2 heavies of the heptameraic? These rely on the analysis and the theory. We have to go back 45 minutes in the talk. Remember the convention that says that heavies may count as if they were light at the beginning of the line. So this heavy, and unlike any of the others, is being crammed into a single grid position. And that's giving it a shorter duration. Empirically, it's what you see in 48 under observed. Here the model is predicting it, and in this case predicting too big of a difference. Overall, the model is doing okay. There are 14 types of syllables in which the constraints actually predict a difference, and we're getting a reasonable match to their durations in the scattergram in 49. I am personally happy with the qualitative behavior of the model, but would like to improve its quantitative fit. It seems likely to me that the weak link in the chain is precisely the target shortcut conjecture, and I'm looking for alternatives. Summing up then, that's the whole thing. I have tried to show that singing in Hausa is a complex, rich activity involving 3 layers of structure, all of which must be understood to understand how Hausas sing: the meter, the sung rhythm, and the phonetic realization, and that constraint-based Maxent models provide a good initial route towards finding an explicit understanding of how these levels work. Thank you.